what happens to a semiconductor when you have electric fields applied? Okay, because finally that's what is going to happen in the device, right? You will take a piece of semiconductor and let's say apply electric field. What happens? Okay, so the schematically something like that is shown here. So you have a piece of semiconductor of length L here, to which we are applying a voltage on both ends. So there's a certain voltage applied. Now what happens? So this semiconductor, could have electrons and holes. Whatever it is, whatever the doping, it doesn't matter for us right now. How will the electrons move? Well, electrons will move towards the positive terminal, right? So in this case, you'll have electrons which are going towards this direction, because this is positive terminal. So yeah, they're going to go towards the positive terminal. What happens to the holes? Okay, so holes will move in the opposite direction. Well, is it that simple? Well, it's not going to be that simple. The reason is we have a lattice full of electrons. They're never going to travel in, will never travel in straight lines, right? If you go to a crowded railway station, you're never going to go straight in a straight line, right? From your starting point to the ending point. You're going to have a lot of people, you're encountering a lot of people, so you have to change your direction multiple times and finally reach your destination, right? So something similar happens. If you consider a situation where you don't have any external field, electrons will simply keep colliding because there is a certain amount of thermal energy, because there is just a finite temperature, let's say room temperature. Electrons will keep moving in some random directions in such a way that, let's say, okay, here this is actually for a hole, but the exact same thing will be applicable for electron as well. So consider a hole which is starting out at, let's say, this point. It gets scattered, it goes in one direction, it gets scattered again, it will go in the other direction, back scattered, so again back. So basically, it starts out at this point and kind of ends up in the same point. On an average, this is never going to be for each electron. Okay, on an average, electrons will simply undergo multiple scattering processes and end up at the same position. So if you don't have any electric field, uh, if you have no electric field, okay, field, then implies random motion, okay, random motion and no net current. Current occurs when your charges move, right? When you don't have a field, there is this random motion, and finally, on an average, there's no net current. But if you introduce a field, okay, so that is what is shown in the blue here. Of course, still there is going to be some random motion, but on a overall basis, there is going to be average movement of charge. For example, here, electron is now getting scattered in this direction, again back, so again here. So the net movement is basically going to be, if you in this diagram, this is the net change in x, delta x, you could say. If you have a field in a certain time, there's going to be a change in delta x. And so essentially what we are having is a velocity that is being created. The velocity, this is called as drift velocity, and we will refer to as Vd, is going to be delta x by delta t. If you give a certain duration, how much is a change in the position? So that's the drift velocity. Okay, so a hole has moved in, let's say, positive x direction here. Electron will move in the opposite direction. And this is what we are referring. Whenever we draw these lines, we are not saying that electrons and holes will move in straight lines. We understand that intrinsically they undergo random motion. But overall, whenever you have an electric field, there's a net drift in the carriers, a drift in the electrons and drift in the holes, which actually occur in the opposite directions. All right. So this sort of a drift phenomena, we call it, the current due to this, we will just, is going to be what? Let's call it J drift, just to distinguish that it is drift current. Okay, current density actually in this case. So how much is the current that is flowing here? So the current is going to be how much is the charge density, right? The charge density is simply, let's call it rho. Okay, and then how much, with what speed is it moving? Okay, this is going to be V drift, Vd we'll call it. So now this is your net charge density. Sorry, net current density. Is it satisfying the units? Please look at that. For example, here in this case, your charge density should be coulombs per centimeter cube, right? And your velocity is going to be centimeters per second. So this is giving you coulombs per second will be amperes per centimeter square, which is essentially charge density. So remember, so we are not taking into account the total current. If you want to calculate the total current, we have to, if you want to calculate I, total current, it's going to be J times area. What area? This is a cross-sectional area. In this space, right? In this space A, in perpendicular direction to the current flow or electric field direction, you have to take, and that you have to multiply to get the net current. All right. So, good. What is the charge density then? Do we know anything about charge density? Well, if you, let's take a uniformly doped semiconductor, then the charge density is going to be simply that which is given by N, right? The charge density is N, or it could be P. Also, P is holes, right? If you have a hole, then it's P. So this is going to be this times the charge, the electron, charge of an electron, right? So this is going to be, this is basically, I can call it density of electrons. And of course, you know what is E, and then multiplied by Vd. This is charge and drift velocity, right? What is drift velocity? The drift velocity is going to be proportional to the electric field. Vd is going to be proportional to the electric field. The reason is, when you saw that whenever you don't have any external field, your drift velocity is 0, and as you increase up to a point, of course, there is a limitation that we will tell you about in the MOSFETs part. But essentially, as electric field increases, Vd increases. So we'll introduce a proportionality constant here. We'll call it drift velocity is basically mu times E. Okay. So this is an important relation that I want you to remember. So what this is telling you is that the drift velocity is going to be proportional, and this proportionality constant, we'll call it as mobility. Okay. So proportionality constant. And this is a term, mobility, we will hear very, very often in semiconductor devices. So what happens is, we will talk about the proportionality constant in just a moment. So what happens is here, J drift is going to be the charge density times the electron charge times the mobility times the electric field. Okay, so this is going to be this. All right, so you can verify that it is still electron. What should be the units? Yeah, this is interesting. What should be the units of mu, so that you have J equal to ampere per centimeter square? Okay, please verify. Okay, what it is. Just a moment. You can pause it if you would like. Just make sure that you get the right units. Never forget the units of mobility. All right. So now, what happens is, we talked about only the electron drift, but the whole drift also is going to be analogous to it. And essentially, what happens in a semiconductor, if you take a piece of semiconductor this way, and let's say I apply a field like this, positive field like this. So positive terminal, negative terminal. So the field in the semiconductor is going to be in this direction. So electrons are going to move in this direction. Holes are going to move in this direction, right, in the positive direction. So by convention, we can take the direction of flow of the holes as the J, current density, J, positive J plus J. Okay, the current is going in that. Now electrons are moving in the opposite direction, but because electrons have a negative charge, the overall current is going to be in the same direction. So basically, because of drift, whatever current flows, it flows in the direction of the electric field. Okay, so for electrons, there is a minus, and then there is a minus E, right? So basically, overall, it's going to still be plus J in plus positive direction. So current, due to both electrons and holes, are going to be in the same direction. So now, because of that, we could generalize the expression for J drift. I'll take the charge of electron out, and so you have the charge density times the electron density times the mobility of electrons plus the hole density times the mobility of holes. And so, and this mobility is going to be material dependent. Okay, and there are a lot of other dependencies as well. So, for example, mobility is, in a way, it is measured by how many scatterings are occurring. For example, think of yourself in a busy railway station. Okay, if the number of people is more in the railway station, the speed with which you are going to walk is going to be smaller. So the mobility of a human being in a crowded railway station is going to be smaller when compared to mobility of a person in the empty field or somewhere, right? So that is one measure. So basically, this tau is going to be the time between collisions. Okay, collisions, and if this is going to be effective mass. If your effective mass is high, then the mobility will be low, and vice versa. So these are kind of you could qualitatively understand what these are. Okay. So now this mobility is, I said, is a material parameter. It is going to depend on temperature. It's going to depend on carrier density and many other factors. But here are some numbers which are very commonly accepted. At temperature T equal to 300 degrees, the mobility of electrons in uh, silicon are going to be 1350 centimeters square per volt second. Please make sure that you got this. Okay, I asked you to verify what are the units. The units of mobility are going to be centimeter square per volt second. Okay, so the mobility of electrons is going to be 1350, and mobility of holes is going to be 480. Okay, this is the typical number for electron for silicon. Why is the mobility of holes lower than mobility of electrons? One way to qualitatively understand is to go back to the bonding picture. We talked about the silicon lattice, right? And then we talked about the bonds surrounding the silicon atoms, and there are these bonds, right? Where are the electrons moving? When we say electron is in the conduction band, we mean that electron can go wherever it needs to go. I mean, it's free to move around in the lattice, so it has high mobility, right? Electron is basically anywhere, right? It could be, and it's free to move around, so it has higher mobility. But what is the hole? The hole is simply going to be the deficiency of an electron here, right? This is basically, let's say, positive. You just removed an electron, that's why there's a positive. Or it could be a deficiency of electron here. So the holes are effectively closer to the lattice sites. Okay, holes are effectively closer to lattice sites, and hence feel higher crystal interactions, crystal forces, you can say, or lattice forces, whatever you want to call it. Let's call it lattice forces because they call lattice sites. And because they feel this higher amount of force, the impact of the external field is going to be smaller. And after all, the mobility is essentially capturing the impact of the external field. Okay, so because of that, you could qualitatively understand that the mobility of holes is going to be small. All right. Well, this is true for most of the older generation technologies, up to about even 45, I would say. But now, with the new technologies, this is no longer true, and there are some corrections that are being done. I mean, we have to. Anyway, you will not encounter this in this course. Only if you do research in advanced semiconductor devices, then you have to worry about that. Okay. All right. So we have seen current is like this, right? So this also gives us an opportunity to go back and revisit what we talked about in the first lecture. We talked about the conductivity or resistivity of a semiconductor, right? So if you see, J is equal to sigma times E is essentially Ohm's law. Okay, you can write it as V equal to IR, and then you can do some manipulations, and you will end up with this. J equal to sigma E is essentially Ohm's law in a different form. Okay, I leave it to you leave that to you as an exercise. Okay, so from this, what it implies is sigma is going to be E times N times mu N plus P times mu P. Okay. This is your conductivity of a material. And so if you know the doping density, you could calculate this. Okay. For example, what is the, I mentioned, resistivity of intrinsic semiconductor, right? Intrinsic silicon. Rho intrinsic For silicon was, I said it will be hundreds of kilo ohms or kilo ohm centimeter. Okay. Verify how much it is. Okay. So for intrinsic semiconductor, Ni equal to N equal to P, right? And you have the mobility here. So if you want to calculate resistivity, resistivity is going to be 1 by sigma. That is going to be 1 by charge density times, this is Ni, times mu n is going to be 1350 plus, this is again going to be Ni, so plus, sorry, into 480. So this will turn out to be something E Ni, and 1350 plus 480, 13 plus 4, 17 plus 50, 1750, 1830, right? Estimate how much this is going to come to, okay? And see what the resistivity is for intrinsic semiconductor, okay? And before I stop, I said that temperature and doping density are going to influence your mobility. I'm really not going to talk in detail about this. If you want, there are sections in the textbook which you can look at. Of course, if your temperature increases, the crystal is going to vibrate, stronger and stronger, because of that mobility reduces. And if you have doping density, you can think of it like the larger number of people on a railway platform, the slower you're going to move. The mobility is going to reduce as the doping density increases. This is very, there are more subtleties to it. It's not that simple. And the last thing, is also, it's also dependent on the surface. For example, if I take a piece of semiconductor, let's say I'll take a small rectangular bar of semiconductor. Well, I'll actually make it into a bar. So let's say you have a semiconductor of this form, right? What happens to its mobility? Well, the mobility in the bulk of the semiconductor is going to be different from the mobility on the surface. Now, for example, I take this top surface or this surface. Okay, what will be the mobility? Will it be the same as a bulk? Of course not, because on the surface you have this unsatisfied bonds. They're not going to be like four covalent bonds, right? Or eight electron shared, right? It's not going to happen on the surface because of this. We call them dangling bonds. Some bonds which are unsatisfied. Because of that, it will not have the same mobility. Okay, so surface mobility is smaller than the bulk mobility. Okay, and yeah, we could talk more about it, but anyway, let's we'll come back anyway. We'll talk about, when we talk about MOSFETs, we're going to introduce this again one more time. Okay? All right. So now let us see how you could calculate these numbers once for yourself and verify. Take a couple of examples. Here there is a plot of resistivity versus impurity concentration for silicon. Okay, 300 degrees Kelvin in silicon. So take a few numbers. For example, take 10 power 16 and calculate the resistivity, and take 10 power 17 and calculate the hole resistivity. Okay. So sorry, if you have holes, impurity accepted concentration of Na 10 power 17, what is the resistivity? If you have donor type doping of 10 power 16, what will be the resistivity? You compute these numbers and verify that this is accurately coming. Okay. So you see that if you look at this y-axis, you are having resistivity of 10 power 4 and 10 power minus 4 in the bottom. So you see this 10 power 8 orders of change. And this is what I showed you in the first graph of the course, that in a semiconductor, you can have a resistivity that can be tuned over a large range of numbers. And that is why they are very, very interesting to us. So you see that as the doping concentration is low, you have large resistivity, and as it increases, the resistivity drops. Of course, we are showing 10 power 21. That is a very, very high amount of doping. Okay? When you go into that regime, it becomes more tricky. Okay. So now I'll ask you one question. At what doping is the resistivity of silicon maximum, right? You might be tempted to say that, well, resistivity is going to be 1 over sigma, and that we have seen the expression in the previous case. So you might be tempted to say Ni equal to N equal to P is the intrinsic carrier concentration. maybe the resistivity will be peak there, right? Well, you have to be careful. This is not going to be the answer. This is not going to be the answer. Okay. To do that, you have to write out, let's say you could talk of resistivity maximum or the conductivity minimum. Both are same. So I'll say conductivity minimum. Sigma is going to be what? N times mu n times plus P, mu P. And the whole thing is multiplied by charge density E, right? So, but you remember in equilibrium conditions, this is going to be Ni square by N. Okay. So substitute, you can find out what is d sigma by dn and you get it to 0. So you'll get the density at which your conductivity is going to be maximum. Okay. So I will leave it to you as an exercise, calculate where the conductivity is going to be minimum. That means at that point, resistivity is going to be maximum. It's not going to be at n equal to p equal to ni. Okay. Anyway, yeah, it's an exercise for you. Well, okay. Let me quickly try to introduce another concept. I probably will not be able to complete it today, but I'll come back to it in the next lecture. Okay. So this is semiconductor. If you have it in an electric field, what happens to the bands? Okay. So we saw this picture already. So let's say I take a piece of semiconductor. I apply a certain voltage to it. I do this. I apply voltage. And then if I do this, what happens? We said already that there's going to be the drift, right? We've talked about this already. So the drift, the field is going to be in the semiconductor is going to be in this direction. And so if the field is in this direction, the holes are going to move in the positive x, you could say, holes. And the electrons are going to move in the negative x direction. Okay. But what is the acceleration? We talked about the velocity. What is the acceleration? Which way they are moving? Are they going to accelerate? Well, of course they're going to accelerate, right? Because we know from Newton's law that ma, right? Or you will take it m star because it's the effective mass you have to take, okay? Not the real mass. Effective mass m into a is going to be what? The applied force, external force. And that is simply going to be the electric field times the charge density, right? And what is the electric field? It's simply going to be whatever voltage you apply divided by the length of the crystal, length of this piece of semiconductor. L, if I call this as L, this is going to be this, right? So you can find out, what is A is going to be sum x centimeter per second square. Right? This is going to be some acceleration. So what it means is, as the electrons move in the semiconductor, they're going to acquire some kinetic energy. Okay. So what we just summarize that electrons and holes acquire kinetic energy as they move in an external field, right? So now we want to capture that in a band diagram. What happens to the band diagram when I apply an electric field? Okay, think about it. So far, what we have seen is band diagrams were relatively harmless, right? They were simply this EV and EC. Now, if I want to represent an electron which is actually acquiring kinetic energy, how will I represent that? Okay, so to understand that, we have to go back once, let's take a step back and think about what happens when you shine a photon on a semiconductor with some band gap. Let's say I'll shine a photon of, let's say h nu equal to Eg. Equal to Eg. This is a photon I shine. So what happens? Well, you had a lattice where electrons are essentially bonded. They are part of the covalent bond, so they are bonded to the silicon atoms. And so I'll apply this photon will transfer its energy to the electron and make it go into the conduction band, right? So an electron which was here in the valence band will actually get, sorry, I should, no, there was a electron here and that would travel up, leaving you a hole and a electron, right? EHP, we saw this before. Now, is the electron in the conduction band moving just after photon is absorbed? Okay, is the, let's say, is the electron hole pair moving, or electrons and holes are moving? I should not say electron hole pair moving. Let's say are E and H moving after absorption of H nu, This is a question. Well, it turns out that they cannot move. The reason is, initially anyway the electron was bonded to the lattice, so the hole was not, the electron was not moving, and it absorbed the energy of H nu, and that was spent in breaking the bond. So it went to the conduction band, but then it doesn't have any more energy, right? Energy has to be conserved. So initial energy was zero, it was not moving. It got absorbed, it absorbed a photon, and that energy was spent in breaking the bond. And so it went into the conduction band, it got free, but it is not moving because it doesn't have any more energy to move. Okay, so it's basically at rest, you could say. Kinetic energy is zero. Now consider another situation. Let's say now H nu is greater than Eg. What would happen? When you have this situation, let's say I'll take the same case. I had an electron at the edge of the valence band, and then I'll make it go into the conduction band. Now, it uses Eg energy to break the bond, but then it has an additional energy, okay? That is spent, basically given to the electron. Initially, electron was here. You took the electron from the edge of the valence band, and you broke the bond. So basically, you have an electron hole pair, but then it goes deeper into the conduction band, okay? The reason is you have this additional energy. So Eg energy was spent in breaking the bond. The additional energy which is there, right? This amount of energy is going to be H nu minus Eg. And that is the amount of energy that it got, and that we will call it as kinetic energy. Basically, of course, it absorbed that energy, it has to acquire some velocity, and it starts moving, right? The velocity of the electron can be calculated. So kinetic energy is going to be equal to incident electron photon energy minus the energy which is absorbed, because of breaking the bond. So this is the kinetic energy of a electron. And you could also have kinetic energy of a hole. I mean, there is no reason for us to think that it's going to happen only from the edge of the valence band, but it could also, you can absorb an electron in the deeper in the band, can absorb, and then it can lead to some situation like this, wherein your hole can have a kinetic energy, Ke of hole, and this is Ke of electron. So essentially what we're trying to say is this excess energy, okay, that an electron and a hole has is represented by depicting it away from the band edge. Okay, I'll write it down. This is important. Let me say this. Okay, the excess kinetic energy after breaking the bonds, okay, of electrons and holes is represented by showing them further from EC and EV respectively. Okay, so what we are saying is, as kinetic energy of electron increases, it's going to move away. If you show an electron deeper in the conduction band, that means has a higher energy. Okay, kinetic energy of electron increases, and here Ke of hole increases. Okay, so we said two things now in this, two concepts. One is whenever you have electrons or holes traveling in an electric field, they acquire kinetic energy. And whenever they acquire kinetic energy, they have to be shown deeper into the bands, maybe deeper into the EC conduction band or deeper in the valence band. Okay, that's how you represent them. So we're running out of time, so this is where I will stop. And in the next lecture, we will start again. We will take off from this point. We will actually draw the band diagram of a semiconductor under an applied electric field. And then we'll also talk about some non-uniform doping and diffusion effects in the next class. Okay. So what we did today was we started out with a brief review of what happened previously, and then we talked about the impact of temperature, and also we mentioned about different impurities and how they impact, and then we talked about the impact of temperature. After doing that, we introduced this concept of compensated semiconductor, and then how to calculate the carrier densities if you have a compensated semiconductor. And then we talked about basically carrier drift, which is an important process. There are two main conduction mechanisms in a semiconductor. One is drift and the other one is diffusion. Okay, so far we covered what is known as drift. Okay, we'll also cover what is known as diffusion, and then we will talk about non-equilibrium situations. Once we do that, we are essentially ready. Our toolbox is ready. Okay. So far, what we've been doing for the last 2 weeks is basically build up these essential tools, and the next week also we'll build up a few more tools. So by the end of 3 weeks, the toolbox necessary to understand the rest of the course is ready with us. Okay. Then we'll apply it to different situations, and then we will understand them. Okay. So that's our goal for the next week. Okay. By the end of next week, we are ready. So in the week after, we will start with PN junctions. All right. That's the plan. So thank you very much for your attention, and I look forward to seeing you in the next lecture. Have a good day.